This is a story of copper, a metal valued by mankind since the Bronze Age, and of universal importance in this modern age of electricity. This story describes the great modern open pit and the mining, concentrating, and smelting operations at Morenci, Arizona, the underground mining operations at Bisbee, Arizona, and the electrolytic refining of copper at El Paso, Texas. It shows the various steps to which the ore is subjected until the copper emerges ready for fabrication into thousands of useful forms. Although the mining of high-grade copper ore in the Morenci District in eastern Arizona began in 1872, a great mountain of low-grade ore lay idle for ages until advances in mining and metallurgical science provided methods for its successful development. Here, exploration revealed an ore body which engineers estimated would yield about 5 billion pounds of metallic copper. However, before regular production could be maintained, it was necessary to remove 50 million tons of waste material, to establish 13 mining benches, to build 30 miles of standard railroad track and 20 miles of truck roads, and to construct the necessary buildings and housing facilities. 5 years of intensive work prepared one of the world's great mines for initial production. This mine is now equipped to produce copper ore at a maximum rate of 50,000 tons per day, and simultaneously to break and remove equal or larger tonnages of waste overburden. Man-made mountains of waste material are gradually filling the nearby canyons. From the benches where the tracks have been laid, waste is hauled away by the trainload. On the higher and more inaccessible benches of the pit, powerful electric shovels load the waste material into motor trucks, carrying as much as 40 tons at a trip. There are now more than 40 miles of standard gauge railroad in the haulage system. Diesel electric locomotives haul the waste trains, while combination storage battery and trolley locomotives haul the ore. New tracks are constantly being laid to permit loading by the shovels into railroad cars. Bulldozers and road graders are used to prepare new railroad grades. And then the new track is laid in its proper place. To speed up the job, the track is laid in sections called panels. These have been assembled in the material yard. After the new track has been placed in service, the old track is removed and the sections that require reconditioning are taken back to the material yard. Extensive repair shops manned by expert mechanics maintain the operating equipment in first-class condition. The sharpening of drill bits used in churn drilling is one of the jobs handled in the shops. This work must be done with skill to ensure efficient drilling. The cycle of ore production begins with the drilling of blast holes to a depth of 58 feet. They are drilled with churn drills, so called because of the churning movement of the drill bit which cuts the hole. Samples are taken of the cuttings drawn from the drill hole. These are sent to the laboratory to be assayed for copper. The assay determines whether the rock is ore or waste. After the drill holes are completed, they are prepared for blasting. Explosives are delivered to a safe location outside the area to be blasted. Only one box at a time is carried from the safety zone to the drill hole. A detonating cord is attached to the primer for exploding the charge. As a precaution against possible failure, 2 primers are used at each hole. These are lowered to the bottom. The required charge of explosives is loaded on top of the primer. This may look like sausage, but don't let it fool you. The hole is then filled with finely crushed rock in order to confine the explosion and cause it to exert maximum braking force. Now the detonating cords from each drill hole are attached to the main blasting line. From 20 to 120 holes may be connected for blasting at one time. At the warning signal, everyone must leave the blasting area. After the area has been cleared, an electric blasting cap is attached to the end of the main blasting line. And finally, the wires from the cap are connected to a hand blasting machine. And then, fire. There goes 250,000 tons of broken ore. Now let's look at another heavy blast viewed from the bottom of the pit. Then this big dipper scoops up 7 1/2 tons of ore at a bite. The electric shovel loads the ore into specially designed dump cars, each holding approximately 86 tons. To protect employees, a water spray lays the dust. This rubber-tired wagon drill is used to drill holes horizontally whenever it is necessary to straighten the side of the bench. Subsequently, the ore is hauled to the concentrator. This involves a 3-mile run through rugged canyon country. Here are miracles of industrial ingenuity, a giant concentrator and a smelter. In these plants, the first steps are taken to separate the valuable copper from its ore. The smelter stack, piercing the skyline, is 57 feet higher than the Washington Monument. The ore being too low in copper content to be sent directly to the smelter must first be treated in the concentrator. Here, most of the waste material is removed. The remainder, comprising about 4% by weight of the original ore, contains the valuable metals. This product is commonly called concentrate. A trainload of ore arrives at the concentrator for treatment. The ore is dumped, a carload at a time, into a giant gyratory crusher. Ore fragments that are too small to require this preliminary crushing are screened between heavy steel girders. Larger fragments pass into the gyratory, which can crush an entire 86-ton carload in less than 1 minute. The ore is then conveyed to a secondary crushing and screening plant. Here in the secondary crushing unit, the ore passes through 2 cone crushers, one above the other, and is broken into smaller sizes until suitable for grinding. Revolving at a steady speed, these huge barrel-like machines, known as ball mills, grind the broken ore to the fineness of powder. The grinding in these mills is done by alloy steel balls the size of a baseball. Each mill contains about 50 tons of balls. Water is mixed with the crushed ore as it enters the ball mills, and continuous rotation with the steel balls pulverizes the ore. The product of the ball mills is a mixture of powdered ore and water. It flows to classifiers, where large steel spirals retain the oversized fragments and return them to the ball mills for further grinding. Fragments that are small enough for further processing are called undersize. The concentrating process requires the use of several tons of water for each ton of ore treated. The pulp of undersized particles in water is carried over a lip at the lower end of the classifier and then on to the flotation machines. Here we see the flotation machine cells in action. The pulp, to which chemicals have previously been added, flows by gravity from the classifiers to these machines. Agitation of the pulp as it flows through the machine is accomplished by high-speed rotation of blades driven by a motor on each machine. This agitation produces bubbles and froth. The heavy copper mineral particles become coated with chemicals and attach themselves to the bubbles which float them to the surface. The lighter rock particles remain submerged. This bubbly froth carries the valuable minerals over the side of the cells. The valueless submerged material, called tailings, flows out at the end of the machine to thickening tanks where the tailings settle and part of the water is drawn off to be used again. Large pipes convey the thickened tailings to these huge tailings dams from which the remaining water is recovered. The waste material that is dumped here gradually fills the canyons. Of every 100 tons of ore treated, 96 tons end up here. Meanwhile, the mineral-laden froth containing the other 4 tons has flowed to this thickener for partial dewatering. It is then conducted to vacuum disc filters, which draw off most of the remaining water. During the process, the concentrate collects on the surface. When the air suction is stopped, the concentrate drops off to a conveyor that carries it to the smelter. Here we see the smelter, which treats the concentrates to eliminate iron and sulfur and to produce unrefined metallic copper. The concentrates are deposited in layers in these long storage piles called beds, with smaller layers of fluxing material. The machine rakes off the ends of the piles, thereby maintaining correct proportions of concentrates and fluxes for delivery to the reverberatory furnaces by conveyors and vibrating feeders. Natural gas is the fuel for the furnaces, and its performance is controlled by periodic tests of the burned gases. With an optical pyrometer, the high temperature of the furnace is measured by the degree of brilliance of the interior. During the melting process, the waste material rises to the top to form what is known as slag. Here the slag is removed and is drawn off into large pots. These pots, each containing 13 tons of slag, are hauled away to the slag dump. Meanwhile, a product known as copper matte has been accumulating in the furnace. This matte, spelled M-A-T-T-E, contains copper, sulfur, and iron. Ladles like this hold 14 tons of copper matte. And along comes a huge crane to carry the molten matte to another part of the smelter, where it is poured into a converter for further treatment to remove iron and sulfur. Air passages are open to admit air, which burns off the sulfur and changes the iron to slag. Here again, slag is formed and poured off. But since this converter slag contains some copper, it is retreated to obtain all of the copper possible. Here the slag containing copper is returned to the reverberatory furnace. The sulfur remaining in the mat has been removed by further blowing in the converter from which copper is now being poured. This copper, now called blister copper, is transferred to another furnace, the anode furnace, where further purification takes place and where the copper is so refined that it can be cast with a flat surface. The final impurities are removed by blowing air in excess through the molten copper. This accomplishes its purpose but introduces some unwanted oxygen. Green tree poles, therefore, are introduced into the molten copper. This represents an old discovery upon which modern science never has improved. The green wood carbonizes and the oxygen passes off, combined with the carbon, as a gas. The final product of all the activities we have seen is copper, 99 3/4% pure. And here it is drawn from the anode furnace and poured into copper molds, 26 of which are carried by the slowly rotating 40-foot casting wheel. 700 pounds of this copper, now called anode, A-N-O-D-E copper, is poured into each mold as the wheel turns. When the metal has solidified, the cast anodes are quenched in a water bath. Rough spots on the anodes are chipped off. The anodes are shipped in boxcars to the electrolytic refinery at El Paso, Texas. Now we visit Bisbee, Arizona, where an entirely different type of copper mining has been carried on since 1880, underground mining. Far beneath the Earth's surface, nature placed extensive deposits of copper ore, rich enough to justify the increased expense of driving miles of tunnels and maintaining extensive hoisting equipment to bring it to the surface. Some of the workings lie more than half a mile below the surface of the ground. This head frame rises above one of the shafts in which 4 cages are operated to transport miners, supplies, or ore. A 5th compartment carries water pipes and compressed air and electric lines. Each cage or elevator car has 3 decks for carrying passengers and supplies. As soon as the workers are aboard, the electrically operated hoist, guarded by elaborate safety devices, lowers the cage at a speed of almost 20 miles an hour into the underground workings. Underground, the miners leave the cage at the various operating levels where their working places are located. Each man is provided with an electric cap light. More than 300 miles of tunnels or drifts have been driven through rock in developing this one mine, which is typical of many underground copper mines. The drifts are continually extended, first to find ore, then to aid in getting it out. Electric locomotives haul as many as 15 ore cars, carrying from a ton to 2.5 tons apiece to the unloading points where the ore is dumped for hoisting to the surface. Doors help control the flow of air which ventilates the mine. Fresh air is needed to cool the deeper working levels and to provide a healthful atmosphere for the workers. For every ton of ore removed, 30 tons of fresh air are drawn into the mine by suction fans. In some sections of the mine, the rock forming the roof and the walls are strong enough to stand without support. Other sections require close support and are timbered to keep the rock in place. Here we find a miner starting to drive a vertical opening or raise which will extend to a level above. He uses a drilling machine called a stoper, operated by compressed air. Big generating plants on the surface of this mine provide electric power for hauling ore and supplies, pumping water, operating ventilating fans, and running air compressors, which in turn operate air-driven drilling and loading equipment. To extend a drift or crosscut, which are miners' terms for the tunnels commonly used to explore ore bodies, this special machine called a jumbo is used. It can be securely anchored by jacks that press against both floor and roof. This jumbo carries two machines to drill the holes for blasting, which will break the rock. Water is forced through the hollow steel drills to trap dust created by the work and wash the rock particles from the holes. When the holes have been drilled, the machine is dismantled and removed from the area to be blasted. On machines like this one, the supporting jacks are easily collapsed, and the machine is readily withdrawn from the working face. Primers now are prepared for blasting. A primer is a stick of dynamite containing a detonating cap attached to a fuse. After the holes are cleaned, a primer is loaded in the bottom of each hole. From 80 to 200 sticks of dynamite may be needed for a single blast. The amount depends upon the number of holes and the hardness of the rock. The miner ignites the fuses with a safety spitter after all the holes have been loaded with dynamite. The spitter, which is somewhat like a 4th of July sparkler, has a definite burning time, and when it burns out, it warns the miner to leave at once for a place of safety, because the spark in the fuse is nearing the detonating charge. After blasting, a mechanical loader is brought in to remove the broken rock from drifts and crosscuts. These are small power shovels operated by compressed air. Their use has eliminated much of the arduous hand shoveling in underground mining operation. When exploration has revealed suitable bodies of ore, the ore is extracted by a method called stoping. This involves the upward extension of chambers or rooms which are opened from lower levels. Slices about 8 feet thick are removed from the roof, which is cut upward at an angle so the broken ore can be scraped readily to a chute. The mining operations in stoping follow the same sequence we have already viewed in drifting. Drill, blast, and remove the broken rock. After the blast, the broken ore from the stope is scraped into chutes which carry the ore to crosscuts on the level below. From this chute, it drops into mine cars. Specially designed sprays eliminate much of the dust and make working conditions safer. Loaded cars are hauled to the shaft station and dumped into the ore pocket. This pocket receives ore from various levels above through chutes called transfer raises or ore passes. Here a sample is taken from each car for assaying in the laboratory to determine its copper content. As a safety measure, dust is controlled by water sprays at all dumping and transfer points. From the ore pocket, 5-ton loads are measured out in what is called an ore cartridge and dumped into skips. These skips, filled with ore, are hoisted to the surface at a speed of 2,000 feet a minute, or about 25 miles an hour. And at the surface, the ore is dumped automatically into storage bins. From the storage bin, railroad cars are loaded. Unlike ore from the open pit mine, which requires concentration, this richer ore is sent direct to a smelter, which in turn produces copper anodes. We now move to the refinery at El Paso, Texas, which receives the copper anodes that are produced by the mining and smelting operations at Morenci and Bisbee, and converts them into the pure copper of commerce. The anodes arriving at the refinery are weighed carefully and sampled to permit assaying their exact content. Here anodes are refined electrolytically. Alternately, anodes and thin sheets of pure copper, known as cathode starting sheets, are suspended in tanks filled with an acid solution of copper sulfate, called the electrolyte. Electric current passed from the anode through the electrolyte to the cathode causes copper to dissolve at the anode and redeposit against the starting sheet as pure copper. Precious metals and impurities in the anode are not dissolved, but settle to the bottom as a sludge. The anodes are being delivered to the tanks by an overhead crane. Each tank is loaded with 37 anodes suspended across parallel copper bus bars which distribute the electric current to each anode. An anode weighs 700 pounds. Here the workmen space the anodes at 4-inch intervals to allow space for introduction of the cathode starting sheets. Careful spacing prevents contact between an anode and a starting sheet, which would produce a short circuit in the tank. These are cathode starting sheets, thin sheets of pure copper electrodeposited on a blank and then stripped off. The starting sheets are attached to copper rods from which they are suspended in the tanks. They are suspended between the anodes on a separate set of parallel bars which collect and carry away the outgoing current. As soon as the electric current is turned on, a careful inspection is made for possible short circuits. After a period of 15 days, the cathodes, plates of pure copper that have built up on the original thin starting sheets, are removed from the tanks. At that time, only a thin sheet of undissolved anode remains. The undissolved precious metals and impurities lie as a sludge or mud in the bottom of the tank and are called slimes. The remnants of the anodes are being taken from the tanks and returned to a furnace where they are melted and again cast into anodes. Strict laboratory control is exercised throughout the entire cycle of operations from the mine through the mill, smelter, and refinery. The slimes are slurried from the bottom of the tank. They are first leached to remove any remaining copper, then filtered, dried, barreled, and shipped to another refinery where their gold and silver content are recovered. Some of the copper cathodes are sent to the shearing department where they are cut into sizes required by the United States Mint or by brass foundries. Some of the cathodes are taken to this casting department. The charging crane handles 7,000 pounds of cathodes at once and transfers them to a furnace for melting. The furnace is charged with 400 tons of copper once every 24 hours. Natural gas is used for fuel. The inside of this furnace is at a white heat. Because air has been introduced to prevent any sulfur in the fuel gases from contaminating the copper, green poles must again be used to eliminate the excess oxygen. This operation is the same as already shown in the Morenci smelter. It ensures copper which will meet the highest market standards. Here a casting wheel 40 feet in diameter casts 200,000 pounds of refined copper into bars every hour. When the furnace is tapped, the molten metal is delivered successively to the 30 molds on this wheel. The molds themselves are made of copper, but are coated with bone ash to prevent the hot metal from sticking. Molds of different shapes are used to produce different commercial shapes of bar. The wheel revolves as the molds are filled, and the newly cast bars are dumped into a water bath for quenching. A conveyor system removes the bars from the water bath and delivers them to the inspection department. And here they are checked for possible defects and gauged for size. This is a king's ransom in copper, weighed, checked, and ready for shipment. Finally, the bars and cut cathodes are loaded into boxcars for shipment to fabrication plants where they will be transformed into sheets, tubes, wire, and other forms for use in manufacture. Every hour of the day, copper is at work for us, for our general welfare and our national security. It forms a network of communication lines for telephone and telegraph systems. It gives us electric light and radio programs. It is a vital part of the ships which support our commercial and our naval power. It makes possible our modern railroad transportation and forms the complex electrical systems of our giants of the skyways. Copper challenges the weather and is excellent as a protective covering. As an alloy, it has joined in noble causes, none nobler than the founding of the Liberty Bell, none more reassuring than its part in giving permanence to this symbol of America.